Okay, good. Um, the reason I asked is because, well, this is a lot of mathematics, and the thing is that the mathematics can be, it can sometimes it can get to be too much, and I might not realize when I'm doing too much mathematics, uh, more mathematics than is healthy. So I want to make sure that you're able to follow. Uh, okay, so all right. Good morning, everybody. Welcome to our um, okay. All right. So welcome to our today's class, number 18, 2020, and we are continuing to talk about coherent states. So far, in this discussion, what we have found is that coherent states are, well, we define them to be eigenstates of the annihilation operator. Then we said that there exists an operator d alpha such that when d alpha acts on the ground state, I get the coherent state alpha. Then we showed that this alpha has certain properties. So d alpha complex conjugate. So it's a unitary operator. And also it has the effect of when you transform the annihilation operator, it has the effect of shifting the annihilation operator by an amount alpha. So this was what we had talked about yesterday. So I think I showed this this fact. Did I show this? No, I don't think I haven't. Okay, so today we will see these properties, and then it has another effect on the A dagger is to take A dagger and shift it by the complex conjugate of alpha. And then we have the fact that if you take the product of two of these, d alpha plus beta times exponent I imaginary alpha beta star. Okay, so ultimately what we want to do is, right, we want to figure out what is this, right? Because we have seen that one can write down a coherent state in terms of the number operator eigenstates. And we have seen that these coefficients C of n can be written as C0 and here's the exact expression, just let me make sure. C0 alpha to be and this should be a 0. Okay, so the thing is we don't have this C0 as yet. We want to find out what this C0 is. So in order to do that, we will need the definition of this operator. What does this operator actually look like? So the definition of this C alpha operator. So this is the definition. This is equal to exponent alpha A dagger, exponent alpha conjugate A times exponent minus 1/2 alpha magnitude squared. Okay, so this is the definition. And now, how exactly do you arrive at this definition? Well, I don't have a derivation as such. I guess that is why people like Glauber are famous, right? Because if everything had a clear path that would take you to that destination, then anybody could find it, right? But there are some places where treasure is hidden, right? And there is no clear path, but somehow somebody or one person or a few people are able to guess where that treasure is hidden, right? Even though you cannot see how to get there. So what we will see is, first of all, that this operator has this property that when it acts on the vacuum state, it will give us alpha. And then the second thing we will see is that we can evaluate this coefficient C naught by using this definition. So to evaluate C naught, what we would need is, right, this is C naught, and we know that alpha is equal to d alpha acting on the zero state. So all we need to do is insert this definition here, and we will get the answer, right? And the answer will actually turn out to be minus 1/2 alpha squared. Okay. So of course, all of this depends on the fact that d alpha acting on 0 is actually equal to alpha. So first we have to make sure that this is indeed the case. Okay. All right. So now we have established these properties, right? That so d alpha is equal to, so one can check directly from the definition. So let's see. So first, let us evaluate these. Let us work out these properties one by one. Okay, so we want to work this out first. Now, one thing is that here, what you have in the definition of d alpha is the product of the exponential of two operators. It's the exponential of A dagger and the exponential of A. So we can use something known as the what I had told you about yesterday, I didn't actually prove it. That there is something called the BCH identity. And the BCH identity, BCH stands for Baker, Campbell, Hausdorff. So it says that if you have two operators, A and B, if you remember, this is the notation for an operator, right? It's a map which takes the Hilbert space to itself. If you have two operators such that AB is not zero, the commutator of AB is not zero, but this guy and also this, these are both zero. So if these are both zero, then we know that A and B will act as displacement operators for each other, right? So what does that mean? That if I take this operation, then this will give me B plus C times alpha, where C is the commutator of AB, right? Because of this condition. And the second condition will imply that B is a displacement operator also for A, right? So this condition implies this, and this condition implies the second line. Okay. So what is the BCH identity? The BCH identity is the statement that if you take so the thing is, before mentioning this, let me first say a small note. Prelude, or maybe prelude is a fancy word, I'll say something else. Sidebar. That for ordinary numbers, right, we have this property, right? Exponent A times exponent B is equal to exponent A plus B. Now, in quantum mechanics, we have exponent A, right? Exponential operators are very common, right? They are very common and they are very important. For example, you have seen one is this translation operator, right? What was the translation operator? It was exponent of minus I delta X P hat by H bar. This is the space translation operator. Similarly, there is something called the time translation operator. What is time translation? It means the same thing. So this is H. H is what? H is the Hamiltonian. We will show this later explicitly. Okay. So you can understand this identity, this expression, because you know that the Hamiltonian is responsible for the dynamics of the system, right? The Hamiltonian leads to time evolution, right? So what is time evolution? Time evolution means how the system moves through time. right? So what is psi, the state of the system at t, t plus delta t, t plus 2 delta t, and so on. So it makes sense that if you think of the evolution of the system as time translation, shifting the system in time, then how should that be generated, that transformation? It should be generated by this. Right? So these are these are all unitary operators, right? So whenever you have a Hermitian this is unitary, and so one can see, right, where there are many other examples of these operators. Other examples, okay, so this is becoming a long sidebar, is a rotation generator, which is exponent minus I delta theta n hat dot j, and then I think that what is this operator do? What is j? J is the total angular momentum operator. We will see this later what this is. And what is n hat? N hat is some three-dimensional unit vector. And what does this do? This says that if you have that if you have a three-dimensional coordinate system, right? You are in 3 dimensions, let's say x, y, and z. Then you consider any arbitrary direction in 3-dimensional space. That arbitrary direction can be given by some unit vector. And then you rotate the system around this axis by an amount delta theta. So instead of delta theta, I can just say theta because this is a finite rotation. You rotate the system by an amount theta around this axis, right? And this is represented by the rotation operator. So you know that any rotation in 3 dimensions, right, can be written as a combination of 3 different rotations, one around x, y, and z separately, or you can write it as one rotation around the given axis, one given axis. We will talk about properties of rotations later on, so don't worry if you are not aware of these things. But the point of all of this is that these unitary operators are very important. The second thing is that these operators, you will always have products of these operators, right? Products of exponent A, exponent B, and so on. Right? These kinds of products will be very common. Why? Because let's say you take an example of translation, right? You want to take the system and translate it along the x direction and then along the y direction. What would happen? So, example, translation along x followed by translation along y, right? And then you might want to rotate it around the z axis. by rotation around z axis. So you can have any arbitrary combination, right? So how would you write down such a transformation? The rotation around the z axis would come last, right? So we'll say rotation around z axis by some angle phi. Then the second one would be the translation around along the y axis by some amount, whatever it is, delta y, where delta y is some finite value, not an infinitesimal. And then you have t of x, translation along the x direction. And all of this would act on the state psi, right? So what are all of these three operators? This guy is this exponential minus I delta x hat by h bar. This is exponent, sorry, not x hat, very careful about that. The momentum, right? Which momentum? So momentum is a generator of translations, right? So if you want to move along the x direction, which momentum should you use? Which momentum? Px, the operator Px. Similarly, here you would have the operator Py, right? With whatever coefficients. Okay. And then this guy would be this expression. And you would get here exponent minus I phi jz by h bar. So you would have the product of these three exponentials. Now the problem is that what you want to be able to do. So let me actually just write out the full form of this momentum translation. Otherwise, some of you might get confused later. This is Py. So right. So and so on. Now the problem is that these operators, they don't commute with each other. So if you have exponent a times exponent b, this is not going to be equal to exponent a plus b, right? Because a and b, they don't commute, right? So if a and b don't commute, then these two operators will also not commute, right? So the question then becomes, is there some expression is there some way to write exponent a and b as exponent a plus b, okay, multiplied by something, right? Meaning that this addition property is preserved, but there is some correction factor, okay? So this is the question, and the answer is yes, there is. That answer is what is known as the BCH identity. So now let me mention. So the BCH identity is the following, that if you have this thing, exponent alpha A, alpha B, you don't need to put alpha, you can just write in terms of A and B, it's understood. Exponent A times exponent B is equal to exponent A plus B multiplied by exponent minus 1/2 commutator of AB. This is known as the BCH identity, and this is a very important identity in quantum mechanics. It is used all the time, so you should know, you should remember this. Okay, so what this is saying is that, right, I can write the product of two exponentials as the exponential of the sum multiplied by this exponential, okay? But this is true. So A and B don't commute. And also this condition is true, that the higher order commutators are 0. So if this condition is not true, then you will not get this simple expression. The expression will become much more complicated. Okay. So the proof of this is similar to the proof of that displacement operator proof that I had shown yesterday, but I'm not going to go into the details. I will share the reference I'm using. If you are interested, you can work through that. So now we can use this BCH identity. Okay. How? We have, if you look at the definition of the displacement operator, what was that definition? It involves a product of exponentials of operators. And these operators, they don't commute with each other, right? A dagger commutator is 1. But because the commutator is a constant, right? Because commutator of A and A dagger is 1. So that's a constant. So if you take the higher order commutators, that means commutator of A with A comma A dagger commutator, you will get 0. So what do you have? Let me write this down here. Exponent alpha A dagger, exponent alpha star A, sorry, and exponent minus 1/2 alpha star. So first of all, this is a direct result of the BCH identity, this expression. Okay, how? So you can, if you write down using BCH, let's say I write down alpha A plus alpha conjugate A. Okay, exponential of these two. Then what is BCH telling me? BCH is telling me that this object, right, exponent, which is this object, this is equal to exponent of alpha A dagger, exponent of alpha star A, right? This guy is this guy, right? And then this I just bring over to the other side, times exponent of 1/2 commutator of what commutator of these two operators, alpha dagger comma alpha star A. So here I have a minus sign. When I bring this exponent over to the other side, I'll get a plus sign, right? And what is the commutator of this? What is this alpha dagger comma alpha star A? Well, alpha is just a constant, so it will come out. So you'll get alpha squared, commutator of A dagger A, which is, so this is going to be equal to minus alpha squared. And so you can write this exponent of alpha A dagger plus alpha star A is equal to exponent alpha dagger, exponent alpha star A, and then exponent minus 1/2. By using this fact, this expression in the second line. So what is this? This is just the definition of d alpha, right? So d alpha is also written in this way as a single exponential, right? How? Using the BCH identity. And again, the reason we can write it in this way is because, so first, let me make sure that I've not made any stupid mistakes. I think I might have made one stupid mistake somewhere. So d alpha is this. Just let me check. Minus sign. So in these notes, maybe there is an error somewhere. Okay, not sure exactly where. There might be an error. So let me just check.
So do we have minus sign in BCH identity? The last term in BCH identity, do we have a minus sign there?
In which identity?
BCH identity.
BCH identity. 1 second. 1 second. No, so this is right. D alpha, alpha dagger, alpha A. Yeah, so this is fine. So if you write it in this way, you'll get exponent of A plus B like this. Now, again, right, yeah, no, this is fine. This is fine. Okay. And now there is another way to write it, which is what is that way? So no, I'll leave. Well, let me see. So the definition, I think I'll have to correct it. The definition, there is a minus sign that is missing. So there should be a minus sign in front of the alpha star. Right. There should be a minus sign over here. This is the definition of the displacement of. So minus 15. Minus again. I know that when you're writing this by hand in your notebooks, it's not so easy for you to make the same corrections that I'm doing. So apologies for the confusion. So because of that, you'll get a minus. Okay. And yeah, let's make sure again. I know this is fine. Exponent this times this. I think there will be a plus sign here now. So there will be plus sign here. Okay. So this is the definition of the displacement operator. You can write it in this way. So d alpha can be written as exponent alpha a dagger minus alpha star. In fact, I suppose this is the easier way to write it. It's easier to remember this. Okay. Now we will work out its properties that I mentioned earlier. So what are those properties? Let's see. Properties. The first property that I mentioned is the fact that it's a displacement operator. That means that this is equal to a plus alpha. So we want to prove this statement. So we can use this expression. Copy. So first of all, we have over here, we have d conjugate alpha. So d conjugate alpha is equal to d inverse alpha, which is equal to d minus alpha. So this will, everything here will just get a minus sign in this expression. So if you put a minus sign, you will get alpha a minus alpha a dash. Okay. This is d conjugate alpha is equal to d inverse alpha is equal to d minus alpha. Then the next term is a that comes in the middle over here. And then finally d alpha. D alpha is alpha a dagger minus. Okay. Okay. So now how do we evaluate this? This looks very complicated, right? You have products of, you have one exponential, then a, then this product. So now if you think about evaluating this directly, it will be a very scary process. So instead, what we can do is we can use the BCH identity, right? So the BCH identity tells us that the first term can be written as the product of alpha star a times the product of minus this thing, right? So from here, this is BCH, right? Times something which is exponent of 1/2 commutator of alpha star a minus alpha a dagger. And so this guy becomes exponent minus 1/2 alpha star. I mean, so I'm just going around in circles now. So I'll just write this is minus 1/2 alpha star, alpha star a, exponent minus alpha a dagger. So this is the inverse of D, right? And just to check, yeah. So D is defined like this. If you take the inverse of this, uh, you get this guy. So this is D inverse multiplied by A multiplied by D. Okay. And then what is D? D is this guy, right? So let's put that over here. Okay. Now in this expression, we have this, we can separate these three terms, right? These three terms become e to the minus alpha a dagger a e to the alpha a dagger. And this is something that you should know by now, right? What is this? This is a displacement, right? So what will this be equal to? This will be equal to a plus the commutator times alpha. And what is this commutator? This commutator is the commutator of this guy and this guy, right? So, okay, and also, I guess, if I'm just going to write, yeah, there's no need to write on alpha if I'm going to write the commutator. C is equal to, and 1 second. All right, what am I saying? This, no, yeah, this is fine. C times alpha, yeah. And the commutator is the commutator of this guy minus alpha star A and E. And this is equal to alpha. So this will become A plus alpha squared. I think so. I'm making some mistake. Okay, so I'll just stop the derivation at this point. The point is that if you insert everything and you work out the commutators carefully, what you will get is you will get this property. You will get that d alpha is a displacement operator acting on A. Okay, so it comes from the fact that yeah, I don't need to do all this. I don't know why I'm doing all this. This is unnecessary. All of this is unnecessary. I can just use the properties of the displacement operator. Okay, so yeah, just let me write this as, this is A, this is B, this is and this is A. So exponent A times B, which one comes first? Exponent A comes first or B comes first? Yeah, A comes first. Right. This is equal to B plus commutator AB. So in this case, this is A, right? And this is minus A. This whole thing is minus A. So what is the commutator of B and A? So commutator of A and B, sorry, A and B in this case is alpha star A minus alpha A dagger, comma. This commutator will be equal to alpha. And so you see that this is equal to A plus alpha by that displacement property. Okay. And this commutator, you can see there is one term with A. That commutator will give you 0. The other is minus alpha A dagger. That will give you -1. Then alpha minus alpha will give you 1. So this is the first property. We checked that. We can do the same thing with the second property, which is what? That D conjugate alpha times A dagger D alpha is equal to A dagger plus alpha star. Again, the proof follows in the same way. This is exponent A, this is B, this is exponent minus A. Exponent A times B times exponent minus A is equal to B plus commutator AB. So commutator of AB, what is A? A is alpha star A minus alpha A dagger, and B is A dagger. What is the commutator of this? The commutator of this is alpha star. Right? So this is also good. Okay, so this is a displacement operator for both A and A dagger. These are the two properties. And then the final property, this D of alpha beta, where is that property? This last property, this I will leave for you as your part of your homework number 5. Okay, so today is the deadline for homework 4, right? So homework 5 will be due 1 week from today. And this also you should prove explicitly. So again. Okay, so these two identities I leave for you to prove. So now I will end today's class with the demonstration that D alpha does actually generate the coherent state given from the vacuum. And so finally, right, after all this song and dance, we can use the displacement property. Okay, how? So let's see, we have alpha, we act on alpha with D minus alpha. Okay, and then we act on it with A, and then this whole thing, and then we put another copy of this thing, which is what? This is just the identity times A times D minus alpha, like sorry, so this will be conjugate will go here, acting on alpha. Okay, so see, what we want to prove is, we want to prove that D alpha acting on 0 is equal to alpha, right? So this implies that D of minus alpha acting on alpha should give me 0, right? Since D of minus alpha is the inverse. And if I act on the 0 state with A, then I should get 0, right? So if this whole thing is 0, then I will know that this is indeed the eigenstate of A, right? So this becomes D of minus alpha, D conjugate minus alpha, A D minus alpha, like this, times alpha. This is the displacement operator. So this becomes A minus alpha. Okay. And so we have A times D of minus alpha acting on alpha is equal to D of minus alpha times A minus alpha acting on alpha. And what is this? This is right, and this is equal to 0 because A times alpha is equal to this. So if you take A minus alpha acting on alpha, this will give you 0. So this means that D of, okay, so we have shown that this D of alpha generates the eigenstate corresponding to the eigenstate of the annihilation operator. Okay, so all of this is okay, but the problem is that we have not yet shown the main thing, the meat of the matter, which is that the fact that why do we call these states coherent, right? So coherent means that they are minimum uncertainty eigenstates. And there is a very important sense in which that makes, in which one should interpret that, which is the fact that they behave very much like classical states. It's not just that they are minimum uncertainty eigenstates, it's that they behave like classical states. What that means is that if I was to take the expectation value of x, the x operator, if I was to take the expectation value of the x operator in one of the number operator eigenstates, what is this? This is 1/2 n a plus a dagger, right? We're talking about harmonic oscillators. Everything is about harmonic oscillators. This is 0, right? So the expectation value of the position in any of the number operator eigenstates is 0. But if you take the right, if you take the expectation value of the position in this thing, in this coherent state, this will turn out to be of the form something like cosine alpha. No, it will turn out to be, sorry, it will turn out to be of the form so it will not be 0. Okay, let me just say it will not be 0. And then we haven't yet talked about time evolution. When we introduce time evolution, then we will make these coherent states time dependent. So they'll become functions of time. And then what will happen is that this will turn out to be, will look like this, cosine omega t. There'll be some phase factor like this. So what this tells me is that when I look at the position operator, right, in the coherent state, how does that position operator behave as a function of time? what happens is that it behaves like this. This is X, this is P. It behaves like this. The position operator goes like this. So the position operator goes like cosine. And the same way, if you calculate the momentum operator, the expectation of the momentum operator, you will get something like sine of omega t minus. So if you plot the trajectory of expectation value of X and expectation value of P, okay, you get the same trajectory as you do for a harmonic oscillator, cosine and sine, moving in a circle in the phase space. The individual positions and momentums are not well defined, okay? At any given point in time, there is an uncertainty delta X and delta P, but that uncertainty is minimum. It saturates, that uncertainty saturates the Heisenberg bound. So this is the sense in which these coherent states, which are minimum uncertainty eigenstates, correspond to classical states. So these are, so this is like the classical. So we haven't talked about this, but there's something called the correspondence principle. The correspondence principle says that for any quantum mechanical system, which is obtained by quantization of some classical system, right? There is a limit when the quantum mechanical behavior will start to resemble the classical behavior in a certain limit, when Planck's constant goes to 0. That is one way of writing down the correspondence principle. So another way is that, well, you should have some quantum mechanical states which behave very much like the classical states. Not exactly, right? So not necessarily that they should behave exactly like classical states. This is the case for the harmonic oscillator. But if you look at some other more complicated systems with more complicated interactions, in that case, you might not be able to construct any states which behave exactly like the classical states, in that they follow classical trajectories in the phase space. But you can write down the evolution of those states as the classical trajectory plus some corrections. And those are the quantum corrections. Okay, so in this case, in the harmonic oscillator, the classical trajectory coincides exactly with the quantum trajectory. And again, keep in mind that as such, there is no quantum trajectory to speak of, okay? Because these are statistical, X and P are statistical, these are operators, right? So when I calculate X and P, this expectation value, I have to do this experiment many times, right? So if I think of this as a statistical property, and so let's say I have X and P, right? And now this is X and P, the measured values of X and P. And I look at the coherent state evolution. So the coherent state goes along the classical trajectory, ideally. Okay. But if I measure X and P at different points along this coherent state trajectory, what will I get? Sometimes I will get this, sometimes this, sometimes this, sometimes this, sometimes this. There will be a fluctuation around this coherent trajectory. Right? it won't behave because it's not a classical particle, right? Of course, then you can ask the question, well, when I make this measurement, will the state not collapse? Will it still remain a coherent state? These are all more very interesting questions, and maybe we'll talk about them at some point. Okay. But the point is that if you take many such measurements, then what will happen? The average of all such trajectories will end up looking like this, exactly like the classical trajectory. Okay, and all of this, so there is the correspondence principle. So we'll talk about that. And then there is something called Ehrenfest theorem. We'll be talking about that also, which gives us a very important criteria for both of these. Quantum to classical transition, right? It allows us, both of these, they allow us to discuss the boundary at which classical mechanics and quantum mechanics, they meet. Okay. All right, I guess this is enough. I'll stop here. So the past, I guess, 4 classes were all mathematics and algebra and stuff. And maybe it was a little bit heavy. But well, there has to be some heavy lifting is involved, right? It cannot all be light stuff. You are all in MSc students, and you're all big boys and girls, so you have to do some weightlifting at this point. Lift some heavy weights, right? Okay, so